Hello everyone, it's March 6th. Alright, let's do this. Alright, let me cancel this. Alright, so what we're looking for is to detect, right, if it has a cycle. Yeah, we know this has been done many times. And I think the accompanying problem is actually more interesting, which is to find out from which node the cycle starts. I don't quite remember how that one done, but I think if I thought about it, I'll remember the solution. But for this one, we just I think it's this node slow, right, equal to head, and list node fast equal to head, and then while I think it's fast is not equal to null, and fast.next is not equal to null. Okay, each time fast goes fast will equal to fast.next and slow equal to slow.next, right? And then we can say if slow is equal to fast, that's when we say return true. Otherwise we say return false. Is that right? Yeah, I think this is right. Let's give it a shot. Nope. Oh, did I do the same thing last time? What's this? Output true should be false. Oh, I think we should do this. And slow is not equal to fast. Right, then we do this, and then we do return slow equal to fast. That should be right. Ooh. Interesting. Oh, because okay. Oh, I can say dot next, right? So long as the fast is running faster than slow, it should be fine. Yeah. Let's try this. Oh, Lord. Wait, so what is this? It doesn't have cycle, right? Then true if it has a cycle, false does not. So if head is equal to null, then I'll return false. I don't know, lately I just keep having these issues. Wrong answers. Keep having these wrong answers. Dear me, come on. Yeah. All right. Try this. I just keep throwing things at it. And eventually it will pass. Eventually it will pass. Get a little bit not careful. Yeah, but I guess it's fine. It's an easy problem anyway. Alright, so this is not the one that we really want to do. This is the one. Okay, this is the one. So we're gonna try Dijkstra on this. We will try Dijkstra. Okay, so how would you do Dijkstra? So Manhattan. I need to find a Manhattan. Okay. It's not DP, I think. It is to do Manhattan. Right, fill out, this is Manhattan. Right, and then we're gonna say, we're gonna try Dijkstra. So Dijkstra, we need a Q. We need also import heap Q. Right. So 26. Q will be this. And we're gonna put in there the starting point 0, 0, and the closeness, right? The closeness shall be the Manhattan, right? So we're gonna do minus Manhattan 0 and 0 and 0 and 0. Okay, this is Q, and we will have DP. So this will record the max safeness, right? Max safeness factor of each cell. Now we have a Q, we have this, we don't need this, and now while Q, we don't do this, we'll get it out. We can say, I'm gonna pop, right? So we can say minus Sij equal to heap Q dot heap pop Q, right? Actually, that's interesting. Is S gonna be positive? Maybe. We'll see. All right, so we pop it out. Then we need to go through the, okay, we'll go through the IDJ. Okay, so we go through the IDJ, and then this is the good one. Oh, check. Right, we arrive with whatever the Manhattan, whatever the safeness, and when we arrive, we have the current safeness, right? We have the current safeness, and it's going to be, so when we arrive, we need to decide what the current safeness is going to be. So we can say current shall equal to the minimum of Manhattan Ni Nj, right? Manhattan Ni Nj, and your S. This is the current, right? This is the current safeness, and then we check to see if the current safeness is bigger than whatever it is in, then we say if the current safeness is bigger than dp ni nj. So if that is the case, then we can visit it, right? We say dp ni and nj is equal to the current, and then we can say heap q heap q dot heap push minus current ni nj. Okay, don't need this, don't need any of this, don't need this as well. But here we have to say while q and q0 0 is actually when I come negative is not equal to dp q0 1 and q0 2. They are not the same, right? Then we have heap q dot heap pop. When I pop it, right? And once it's good, then we do this. What if there's no q? If there is no q, I don't think it's possible. There'll always be something in the queue, right? It will always be something in the queue. Then you would just keep going, and you pop out the current. Then you do this, you push it in, and then we keep going, keep going, keep going. So what is the end? Well, the end is when say if I is equal to n minus 1 and j is equal to n minus 1. When that happens, we simply return s. Invalid assignment. Cannot do that, huh? That's fine. We'll do this. So number negative. That is okay. Right, so this is also gonna be negative. Alright, negative, and then will be this. Okay, that's fine. We'll do this. Otherwise, at the end, what else would we return? Oh, we won't really hit the end. Oh shoot! Yes, I forgot the Q. So what would we return here? We don't return anything. Missing return arguments. Yeah, we return 0. Should never reach this point. Okay, let's take a look. Does Dijkstra work for this giant? Ooh, even Dijkstra doesn't work. Memory. Huh. I'm even not sure if Dijkstra work for these. Index out of range. Well, it will pop everything. Ooh, that is very funny. Well, because you never tried dp first. Yeah, my bad. So dp 0 and 0 need to equal to Manhattan 0 and 0. Took a ridiculously long amount of time. I wonder what happened. Wait, is it really that slow? Yeah, it is very slow. Okay, so we also need to handle, so if it's larger than this, okay, maybe I can say and current is smaller than shouldn't you just use Manhattan? Like, don't use dp, right? Can we just call dp equal to Manhattan? Can we do that? We call dp as Manhattan, because everyone, if you're smaller than, well, no, because if you're smaller than, you still need to go, right? If you're smaller than, you still need to go there and then drop it lower. So yeah, I think we still need to do that. Just when you reach the end, if you are bigger than, and there's no point, because the answer will definitely be smaller than, smaller equal to this one value, right? Well, definitely smaller equal to this value. Therefore, I mean, each point, it's going to be smaller. So I do the minimum first, right? I do the minimum first. And I say, if that's, I'll set it to the current, right? And the next one, if it's bigger than, and it's smaller, right? If it's bigger than this, and it's well, I handle this one first, right? So it will definitely be okay. And we say, because if it's too big, right? If I hit it, it's too big. Then you push this one again. Basically, we have a bigger value, right? We have a bigger value. And we try it again. I think we probably can take a look in the debugger, right? Because it runs pretty slow. Okay. Manhattan. Wait, what? It's 0, 0. I don't want this one. I don't want this one. I think I want... Maybe try this. Wait, is this one correct? It just take a long time. Okay. Okay, well, Q 3 and then 0, 0 is equal, so we get out. So S is -3 and then IJ 0. Okay, for the IDJ, NY and NJ 0, 1. It's a 2. Okay, so current shall equal to a 2, right? Where's current? I don't see current. Here we go. Current is 2. And then Manhattan and NJ is 0, 1. Manhattan is 2. So current is 2. Okay, so dp this become 2. And we push this in. Okay, next N9 and J. Okay, this one get out. Next. Get out next. 1, 0. 1, 0 is also 2. Yep. And then 2 come out, right? Okay, 2, 0, 1. Okay, 0, 1. Okay, we'll try for directions. N9 and J, 0, 2, so we move more to the right. Current become 1. Right, current become 1, yeah. Okay, do 1. 0, 0. Okay. When you hit 0, 0, S is 2. We might be revisiting nodes, you know. We might be revisiting nodes. But if revisiting nodes allow us to get... Yeah, we shall revisit nodes, but this one we don't revisit. So this one is bad. The last one. 1, 1. Okay. 1, 1. Current is 2. So we run this. S is also 2. So current is 2. So we get 1, 1 is also 2, right? Okay. 1, 1 is 2. Right? 1, 1 is 2. Yeah, because this is 2. So we go here, this will be 2. Okay, so we had a 1, 0. So N1 is also 1, 1. Okay, so the Manhattan 1, 1 is a 3. DP 1, 1 is already a 2. And a current is a 2. Don't do. Yeah, this looks fine to me. Right, this looks fine to me. Every time we go through 4 directions, and then we check if we can get it bigger. I mean, the only thing we can say is maybe if we, I don't know, instead of check it here, right, we check it here, right, if it's good, and if this, say if ni is equal to n minus 1, and nj is equal to n minus 1, we'll return current. I think this will save time. I don't know. It's just the first time it happens, so we just get out. Yeah, I don't think it'll help. That is not the issue. Huh. So what you're saying is you at least let them do once, right? If they have hit it once, you hit them again. Uh-huh. Okay, so how about I set these start with -1. I say if this okay, so if dp ni and j is smaller than 0, okay, or this is larger than and current is smaller than Manhattan n minus 1 n minus 1. So if that's the case, okay, if that's the case, we'll only do if it's smaller. If not, nothing, then we will return Manhattan distance at the end. So basically just say every path that we take has it bigger. And now we put these conditions. Syntax error. I think I forgot another parentheses. Okay, let's see. Does this one work? Oh, shoot. Yeah, or. Still not right. I'm out of ideas. Try this one. Binary search, BFS, union find. What? Union find? Both BFS and binary search together. Okay, BFS and binary search. So it's kind of to see if it's possible, right? Because we want to find the maximum safeness factor. So we can set a safeness factor. We can set a biggest one, which we can obtain from doing this. So we know the biggest one. So we have the smallest one is 0. Then we set in the middle, right? We say, okay, can we go from top left to bottom right given this? So we BFS it, and whenever a path, right? Whenever a path gets smaller than the target, we just nix it. And that might actually work. That actually might work, man. Okay, so not Dijkstra. Dijkstra doesn't work. But this new idea of now BFS with binary search. All right, so low is 0, low and high. Right, low high shall be 0. High shall be at most 2n. Right? Actually, it's not. So 1, 2, 3, 4. At most is n plus n minus 2. Right, because there's n minus 1 on this, and n minus 1, so n minus. So we put it to n, which is fine, because we want it to be a little bit bigger on both sides, actually. Yeah, on both sides. So let's set to negative 1. Okay, so then we say while low is smaller than high, mid is low plus high divided by 2. Maybe. Yeah, if it's not possible, I will high of the mid, high to mid, and eventually this was this high to mid, and we get out. So we return a low, right? Yeah, so it's too high, it's not possible, so we get a bit lower. Is it possible? If it's possible, then it will be mid plus 1. Right, mid plus 1, and then it's not possible to go minus 1. Okay, let's try. Now we're gonna go BFS. Right, so we say Q shall equal to 0, 0, Manhattan, 0, 0. Okay, and then we can do a visited set of 0, 0. Right, so while Q temp for J D safeness in Q. Okay, then we shall say if I is equal to a minus 1 and J is equal to a minus 1, then we'll break it. Might as well just write a function called call. So I want to know is it's possible or not, right? So I might just say def BFS, right? All we want is we have a threshold, cannot go beyond that on a safeness, and that's about it. Of course, pass grid. Okay, and this one we will return a Boolean value. Okay, BFS. Oh, we also need Manhattan. So we have a grid and we have a Manhattan. So list of list int. That's fine. And we will copy and paste all these code. Wait, why black is not working? Because the code is not formatted? I thought I have auto format set up. Wait, I thought I had it set up. Yeah, it's set up. I don't know. Nothing changes. Alright, doesn't matter. So I have visited, so I'll queue this. ON is not defined. That's fine. So if this, then we simply return true. Right? BFS is possible. We have hit the target. Otherwise, then we do for what's the same thing as this one. The IDJ. Can we fix this? You say we just can't. I don't know. the formatting doesn't work. Now it works. It's okay, it's weird. Alright, anyway, so we have in and J. J is possibly unbound. Oh, we bound. I don't know why they say J is possibly unbound. J is here, right? Okay, so this we need to change. So if this, that means we can move on. All we want to do is to find, right? All we want to do is to find the next, right? So we say next S shall equal to basically a minimum of the current S and Manhattan in I and J. Then we say if next S is smaller or equal to the threshold, right? Because we want to reach that. Then we can do this temp dot append this. Of course, we say next S. I don't know, why would you say they're unbound? They're here, they're bound from here. And Ni and J, right? Not in visited. So do this, and then we say visited dot add Ni and J. S is possibly unbound. Oh, it is unbound because it has to be this way. Alright, once we're done, Q equals to temp. Keep going until otherwise we'll return false. Okay. Now for here, we just say if self.bfs threshold is mid grid Manhattan. If it's true, which means we can reach, then we can move the low higher, so low can equal to mid plus 1. Else, then high needs to be low or high equal to mid. Right, we keep doing this. We return low minus 1, I think, right? Because we tried, eventually we get out is going to be high equal to mid. So either low plus 1 gets up, right? And then it should be low minus 1. Or maybe it's high is not working, right? The high is not working. Well, a high is not working. What do you mean by high is not working? It's just false, so high need to go to low. And then it's not working. Yeah, okay, let's try this. 51. Does it work? Huh. This one's still not working. How about the other ones, the easier ones? They work Do they work? No, they don't even work. That is hilarious. That is truly hilarious. I don't know, why is it not working? Yeah, I say I'm just gonna BFS the whole thing, right? I BFS the whole thing, and then every time they reach some stuff, they will get a minimum out of it. Yeah, maybe it's more than that. Maybe we shouldn't just get a minimum. Maybe at each point, we need to still record. Maybe we should still record it. You know, because the ideal is every single time you want to go to the next one. Because I say you cannot go beyond, right? You want to find a maximum. So I give a value, right? I give a value. So what we're saying is this the maximum safeness factor, right? Which means as we go through, the safeness factor, wait, hold on, the safeness factor should be cannot go beyond the threshold, right? Yeah, it cannot go beyond the threshold. Or, wait, it cannot be smaller. It's not, it should be bigger, right? If I give myself a threshold and everybody is bigger than this, yeah, I think this should be larger equal to. If everyone is larger equal to this threshold, then yeah, we just keep going on. If it's smaller, then you will bring a small. So what we'll do is larger equal to, right? And if it's true, then we can make it even, we can make it bigger. Yeah, okay. So I changed that from smaller to larger. Okay. Now these are working. Okay, it's hilarious. We're gonna try this hilarious one. Been trying it for so long and it never worked. Never worked. I think it's still not gonna work. You're kidding me, man. Memory exceeded. Ugh. Is there some way we can reduce the memory usage? I mean, I am visiting the queue, right? I am visiting the queue. Can we not use the queue? I don't know. How do you avoid doing that? What you need a grid for? So we have the Manhattan, so we can release the grid. Yeah, you don't need this grid. I never use grid. Oh, we have Manhattan. Right, we can use Manhattan here. I don't know. I remember something like maybe del grid. I remember something like this is to release something from the memory. But I don't think that's the issue. No, the issue is with the BFS. Because of the visited. Maybe that's the reason why it timed out. Okay, let's try some others. You know, just take a look. Oh, it's not even correct. This is not even correct. What? Is this correct? Alright, the first one is wrong. Output 6, expected 5. Huh. Which part? Yeah, so we start from top left, okay, and then we try, and then we got this, and we try the next is not even visited. Then we get the minimum value, right, with the current S, with the current safeness of this path, and with the Manhattan value. So the Manhattan value, if it's smaller, then we take the smaller one. And then we check if it's larger or equal to the threshold. If it is, then we say we can visit the next node, right? Everybody's above the threshold. If it's smaller than the threshold, we simply don't do it. Yeah, we go through all this. We get out, Q equal to temp, then we try it again. And eventually, in one of the step, right, if I and j is equal to n-1, that means we hit the bottom right. Right, we hit the bottom right. And if we hit the bottom right, we say good, right? We hit the bottom right. And yeah, that would say true. Otherwise, we say false. I don't know. I mean, the method seems very straightforward, but it is not working. Maybe, okay, it was just a guess. Maybe I don't use a set, you know? Maybe I just use 0 times n for this in range n. Okay, so we just say and visited is equal to 0, right? Visited and not visited ni and j. Now I say visited ni and j is equal to 1. That could be a way. But this will still be wrong because I don't think the problem is with this for this, right? What is the issue with this? Anything with this? I mean, that could be a guess, maybe. But I also don't think that was the issue. Yeah, that was not the issue. And I do think -1 is a better option for this. But then what? Huh? Then what? The Manhattan distance is correct because I used this method previously and it worked, right? So Manhattan is correct, and we are basically just going through the we're basically just going through just BFS the entire thing. And how did we do wrong? I'm always pushing the current S, right? The current Manhattan distance. We have ij and the Manhattan distance, which initially is the safeness, and then we reach every single node, which will take the minimum of it and nj. Okay, yeah, this is like the next safeness value, right? If the safeness value is larger or equal to the threshold, then we move on to the next one, and we set the next one equal to 1. We forgot to set visited 0, 0 equal to 1. But again, I don't really think that's the issue. Yeah, that's not the issue. What the hell? Basically, I say 6, right? 6, with threshold 6, I say it's possible, but in fact, it is not. But in fact, it is not. And this one is way too complex to even try to debug, right? We have too many. All we can do, maybe just print. You know, we do some print. Low, high, mid, and we'll run this. Low, high, mid, low, high, mid. 6 is true. See, that's the problem. 6 is true because it's true. It raised up to 7. Okay, so 6 is true. 6 is not supposed to be true. Maybe. For row in Manhattan, maybe. Actually, I can try. I can do this locally. I don't have to do it here. Manhattan. Okay, so is 6 possible? 6, this is not possible. Well, this is possible because it's 7, right? So we start with 6. We start with 6. Ooh, there is one more thing I didn't check. Yeah, I can check it here. I actually check it here, right? So this is the threshold. This is Manhattan, and I can say if Manhattan 0, 0, right? If Manhattan 0, 0 is smaller than threshold, just return false. Okay, I don't think this can change anything, but yeah, I don't think it's gonna change. Still 6. Okay, so it's 6, 6, 7, 6, 6, 6, 6, 6. Over 5, so we keep going 6, 6, 6, 6, 6, 6. Yeah, I can get it. What's the issue? Diagonally, there is a path. Huh. Down, 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 this, down, this. Right, we're all on 6. Okay, then the problem must be the like 1, 2, 3, 4, 5, 6. Like this should be 6. Right? This is 6, it's not 7. Because from this I have 1, 2, 3. This one should be 3. Oh, I think the Manhattan distance is not correct. It's the Manhattan distance part. Okay. That is fine. How do we do the Manhattan distance part? Well, I say everybody is 0. That is fine. And then starting from all of them, Q, D, right? And then I say I set Manhattan to D. Huh. Maybe I can do a minimum, right? Manhattan IJ, Manhattan IJ, and D. How about that? Oh, now we're right. Now we're correct. We need to set it to the minimum. Okay. We still need to run the Holy Grail. Holy Grail is not this. This is the Holy Grail. We can pass anything, but if this does not pass, it's still not gonna be right. Judging. Oh my god. Wow. I am not sure what to do. Maybe we shouldn't do, but we tried it, right? Like if we do it this way, it will run, right? We do it this way, it will run, which means the memory issue is caused by the later thing. Not really. We already have memory issues here. What? Oh, the problem is with something else. Wow. Okay, so the problem is not the BFS. The problem is here. I am creating more. You should do it here. If this is smaller than that, we shall set it to d plus 1, right? Which means if it's bigger or equal to that, we don't put it in. Huh. Still no good, huh? Nope. Still no good. Madre mia. But well, how about the previous? Is this one still good? Man, need to fix. Oh my god. This is not good either. Oh, for sure. It's NINJ. My bad. NINJ. Okay, so now let's go back to the... It's just, you know, back and forth. Back and forth. Now try the Holy Grail again. Come on. Come on. Give me some love. There we go. There we go. It's just a lot of... Oh my god. My goodness. This problem. I don't even know what to say. This problem is just... Alright. I'll do math out. I don't care. Ooh. That's a lot of effort. Right. I had to read the first hint. Let me do this way. I started with a bare bone BFS, but BFS, keeping track of all paths that can potentially get a bigger, safeness. However, it times out. Then I tried Dijkstra. Actually, I am not sure because the issue is with this. So Dijkstra might work. Okay, Dijkstra might work. So then I tried Dijkstra, but due to some technical issues with the computation of Manhattan, that method didn't pan out, but I will try it again. Finally, I went for the first hint, which immediately pointed me to the right direction. Okay, we will simply binary search this, right? Pick some threshold and then BFS the grid and see if it is possible, right, to get from top left to bottom right. Okay, yeah, and then I'll call it ON squared, right? ON squared log n. I do want to try Dijkstra. Okay, we'll try Dijkstra. Like for sure thing, we have to try Dijkstra. Okay, this one passed, but yeah, it counts as a hint. Yeah, I kind of regret it. Yeah, I know. That's why I'm gonna complain. That's fine. All right. So let's just do 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. Then you won't complain. Okay. All right. That's for today. And but this one needs more love, right? I need Dijkstra this, for sure. I need a Dijkstra this, because I still believe Dijkstra will work. Okay, I still think Dijkstra will work. All right. Anyway, that will be it. I will see you guys tomorrow.